you for recording the meeting Zoom, and we are doing an inferential statistics review. And the midterm exam that we took covered descriptive statistics and a tiny bit of inferential statistics because we were looking at linear regression lines there. Since then, we've done probability. We've done confidence intervals. We've done hypothesis tests. And then for hypothesis tests and confidence intervals, we've done them in two different ways. We've done them with randomizations through StatKey. And then we did them with the central limit theorem in a spreadsheet. And so the final exam is going to be this stuff. There's going to be a little tiny bit on probability, but mostly it's confidence intervals and hypothesis tests with randomizations and a spreadsheet. So I am going to jump right in with a hypothesis test, which I think is about the most difficult thing we do. And we're going to do it both with a randomization and with the central limit theorem. So from last week's homework,
Probably disagree. I think the probabilities are way harder.
The probabilities, yeah, probability is, you know, it is wicked hard once you ask an interesting question. But I'm just going to keep it really simple. And if you look at the practice problems I put on the final practice, there's just a few simple probability problems. And I will review at least one of those today. And I got one email so far about those kinds of problems. Oh, we got chat going on. Yes, yeah, no doubt. The wording I have to rethink, and not only just probability, but for a hypothesis test, I gotta, when somebody presents me with some information about one, I gotta read it several times to figure out what's going on. Whether it's in a statistics book or in some real situation. Like I was trying to look at differences in resistance to getting COVID if you had COVID recently or if you got the shots, and data is still coming in on that. We're still figuring it out, and reading those reports is kind of challenging some days. All right, let me see. I'm looking for the mice one. I think it was number 5. No, it wasn't number 5, but that's another one I'm going to do. I'll come back to that. Number 11. How about that one? Here we go. Load this up. So we're testing a claim that having the lights on at night increases weight gain. This problem is presented in the book also. The data is available on StatKey. A sample of 10 mice lived in an environment with bright light on all the time. 8 mice who lived in an environment with the normal light-dark cycle, and their data on weight gain is given below. We're going to test this claim using a 10% significance level, assume the population variances are unequal. We haven't talked about that, but that's something that comes up in statistics, and you would see that maybe if you got to a second course on this. I just state that in there in case other people use my homework, other teachers, that the weight changes are normally distributed. Okay. And the idea about the weight changes being normally distributed, I kind of need that if I'm going to use the central limit theorem, because I have small sample sizes here. So the central limit theorem says if our sample size is 30 or greater, then we can just go for it. Otherwise, if the sample size is smaller, then we hope that the population that these numbers come from are relatively normally distributed, so that repeated sampling leads to bell-shaped curves. All right, so let's do it. At the moment, really all we need to do is jump into StatKey and find this data set. So blow this up a touch. That is readable there. And then randomization test difference in means, that's the right spot. and I want mice weight gain. Okay, so the data is here, and it's organized a little bit differently than I presented it. So this is the way StatKey likes the data. One column is the categorical variable, and the other column is the quantitative variable. In a spreadsheet, you can do it with the data organized that way. Typically, when I do a spreadsheet, I have the data organized in 2 columns like this, but it can go either way. We'll do a spreadsheet in a moment. All right, so close that, and here we can see that when we look at a difference of means, the hypothesis, null hypothesis, is that there isn't a difference. And the alternative either is that one mean is greater than the other, one mean is less than the other, or they're just different. But the null hypothesis is that the difference is 0, that there is no difference here whenever we look at difference in means and difference in proportions. Here I have my sample statistic, which is the difference in these 2 sample means. And so this particular group of 10 and 8 mice had a difference of 2.62, and that's the difference in each of their averages, 6.732 minus that 4.114. So just some of the numbers that are important. And really in StatKey, we just need to generate, because StatKey already has my hypothesis and it already has my data. And it's a good idea to do at least 5,000. I usually do 6,000 or more. And again, what just happened here? What are all these dots? Every dot here is a reshuffling of this data right here. And the way that works is we basically kind of throw away who was dark in the dark and who was in the light. And then we pick randomly 10 of these, and we pick randomly to be the light mice and pick randomly 8 of these. And we see what kind of variation could happen given these kinds of weight gains right there. And so we get a lot of different variation in terms of the difference. Sometimes the dark mice gain more weight, sometimes the light mice gain more weight. But on average, we're assuming there's no difference, and that's the 0 in the middle, the null hypothesis, that the difference is 0. Here, I gotta figure out if I'm doing a left tail, right tail, or 2 tail. So there's 2 more steps to get a p-value. So I gotta read the problem again. You're testing the claim that having the lights on increases. Okay, so they're giving me a greater than probably if this is light minus dark. And the light, the lower one here, is x1 bar, and the dark is x2 bar. So yep, they're in the right order. Double check that by looking at the data. Light comes first, dark comes second. So the computer's finding the average of the lights, the average of the darks, and then subtracting them. All right, so that means I'm doing a right tail test. Let's regenerate. 8,000, that looks good. Okay, now just clicking right tail isn't enough because I have to enter my sample statistic. So the 2.26 in the difference in the means has to be entered down here. And that's one of the most common mistakes, is forgetting to enter the sample statistic in StatKey. So generally when somebody writes to me their p-value wasn't right, I can probably pinpoint it to missing that last step. So this tells me that if we expected the mean to be 0, no difference, the probability of getting a difference of light minus dark of 2.62 or more, could be a higher difference, is about 1.8%. So I'm just going to screenshot that, stick it in my whiteboard. Let's see, I guess I'm going to do this part. And the original data would be nice. So what's going on here? Labeling some stuff. This is my null hypothesis, that mu1 minus mu2 is 0, that there's no difference. That's equivalent to having a t-value of 0. And then we'll get to a t-value when we do the spreadsheet. StatKey doesn't provide that. This number right here is my sample statistic. And often, although I'm working on a computer, in my notes, I'm drawing this out on paper too. Statistic. So I'll draw that in a second. And this number up here, provided I have my sample statistic, is the p-value. So the p-value has to have the sample statistic, not some random number StatKey throws in there. So this right here is the p-value. And in a randomization test, it's the percent of other samples reshuffled from that one that had a higher difference in means. out of my 8,000 samples. And on my paper, in my paper notebook, I'm usually drawing something out where I draw a smooth version of this. In the middle, I put whatever my null is, 0, mu1 minus mu2. And then StatKey tells me that this is between 2 and 3 standard deviations away. So about here-ish is my 2.62. And then the p-value is this whole region over here. 0.018%, sorry, 1.8% of other samples end up with a higher difference. That's the p-value. So my p-value is small. Remember my significance level. Let's write down the hypotheses here. H0, mu of the light mice is equal to mu of the dark mice. And StatKey was calling them mu1 and mu2. Alternative hypothesis is that the average weight gain of the light mice is greater than the average weight gain of the mice that were in the dark. And I was asked to use a significance level of 10%. And here I can see my p-value is definitely smaller than that. And so that implies I should reject the null hypothesis. And rejecting the null hypothesis, that's the decision, which is kind of meaningless on its own. What does it mean to reject the null hypothesis here? Well, it means the data supports the alternative that the average weight gain of mice that were exposed to light all the time is greater than the average weight gain of mice that were in a regular light dark cycle. I'll type that out in just a minute. So again, I ran my hypothesis test. I have my decision right here. And so the last two things I like to do, and I've asked you to do on the applications, is say, okay, what does the conclusion mean in plain language? Don't mention the word null, don't mention the word alternative, just tell me what this means. And then the more technical aspect is, what does this p-value mean? And I said it a couple of times. I'm going to write that out in a moment too. Before I do that though, I want to try this in a spreadsheet. I'll show you how to use the spreadsheets we've been using to kind of do the same things, a similar thing to what StatKey did. Now, I happen to provide the data in a way that the spreadsheet likes it, at least my spreadsheets. It can be done with the other formats StatKey has. So what I could do is copy this and then paste it into a spreadsheet. And so I already did that. Before class, I grabbed this data, and I highlighted it, copied it, went over to my Inferential Statistics spreadsheet here, and I looked for, again, we were in StatKey, a difference in two means. I looked for one of the tabs down here that was a difference in two means. And eventually I got over to here, two mean hypothesis test. This was one we did about smiling versus neutral in class last week. And I just duplicated it. And that gave me a new one that I relabeled mean hypothesis test mice weight. And so I will reshare this in case any of you don't have this spreadsheet handy. I would highly recommend having this spreadsheet handy when you take the final. I'll show you later a few things that I would recommend having handy for the final. I'll put this in the chat if anybody wants it. Okay, so this is the same spreadsheet I've been sharing for the last few weeks. And there's tabs at the bottom for every kind of test or confidence interval that we've done so far, and a few extras that I've included just because they were in videos. Earlier, I had pasted it in from StatKey. That's what this is. I really don't need that right now. Here it is from our homework, pasted in. So once the data is in there, so all I did was delete these two columns. Oops. And repaste my data on top of it after I deleted them. It's always safe to delete first, then paste second. Do that. Someone's looking for that. All right. Once you get your data in there, then the spreadsheet's set up to count each data set, to find the mean of each data set, to find the standard deviation of each data set. And then down here, it gives me my x1, x bar 1 minus x bar 2, which I usually call the sample statistic.
Can you zoom the screen a little bit?
Yes. Like that. How's that look? Better?
Yes, thank you.
Okay. So I just asked the computer here to subtract the means, and you got to make sure you get those in the right order. And often they're given in the right order, but sometimes I always kind of double check because once in a while that can go wrong. Degrees of freedom, there's a complicated version of that, which I haven't talked about. It's usually covered in other statistics books, sometimes in the first course, sometimes in the second. It's a crazy formula I've included there. We're not going to use it, but in case you ever need it in the future, there it is. We're using the simple version of finding degrees of freedom, which is take the smaller sample size, in this case 8, and then subtract 1. Spreadsheet does that automatically for you. Automatically calculates the standard error here. That's a bit more complicated than other standard errors we've done, so it's kind of nice the spreadsheet does it for me, where it squares the standard deviation divided by the sample size, adds that to the square of this divided by the sample size, then takes the square root of that whole sum, and finds the t-value for you. So here I can see the t-value is about 2.4, and that looks about right here. It's between 2 and 3. And I take it back, these aren't t-scores down here. These are actually differences in weights of mice is what StatKey is graphing. Mistake over there. Now the spreadsheet doesn't automatically find the right p-value, so the previous one I copied this from, let's see, where did this go? Was a two-tailed test, so I had to modify the formula here. So at first it was giving me the wrong p-value because it was using the two-tailed version. I had to jump in and rewrite it to say, hey, use the right tail version. So on this particular sheet, you do have to double check you have the right p-value. Since it is smaller than my alpha, oh, I have a different alpha on this problem than the last one. My decision is to reject the null, and then here I write what that means. I'm just going to blow this up again so you can read that. So here's what I thought the conclusion was. We have strong evidence that the mice exposed to light all the time rather than a natural light-dark cycle gain more weight than, I should say, than mice exposed to a natural light-dark cycle. So I'm just trying to take the information about what sample and populations I'm talking about and put the sample and population into the context of this particular problem. I don't really need to mention the sample size. I don't need to mention the p-value. I don't need to use the phrase null or alternative hypothesis. I just want to kind of state it in plain language. What does this decision mean? And that's always the hard part. It takes me a couple drafts to get those right. A reminder about what the p-value means. And the sketch kind of helps me figure out what the p-value means. So the p-value, again, is this region over here. And we came about that region for a couple of reasons. One, we assumed that the middle was a mean difference of 0. And two, my sample had a mean difference, or sorry, difference in means of 2.62. And given the sample sizes, that's how far 2.62 is away from 0. Such that other samples, there's about a 1.8% chance that another sample, kind of like mine, would have a bigger mean. So I'm gonna type that out. So this, what I'm gonna type, actually, I might as well type it. Although Spreadsheet's a horrible place to type, because it's got these weird little tiny boxes. I guess I'm going to write it out. So this is an interpretation of a p-value. Which is totally different than a conclusion. So in this case, there is a 1.8% chance finding another similar sample with a, and this is a difference in means that we're looking at here. So that comes next, difference. That is more than, higher than, greater than, anything like that, because it's a right tail test. This difference in sample means. And I'll often state that 2.62 when we were expecting no difference. And so I got to put in the null there too. So basically this describes the graph that I have of the p-value and how the computer and I came up with that 1.8. All right, so we've done this in a couple of different ways. Now something to point out here, this p-value is about 2%. And the p-value from the, so that's using the central limit theorem formulas. Using the randomization test, I get about 0.018, which to the nearest whole percent is 2%. So are they the same? No. Are they similar? Yes. And the central limit theorem says they should be close if you have a high enough sample size. Now, I don't really have a very big sample. I've got 18 mice altogether, but I'm still pretty close on those p-values. If I regenerate these, so reset, do it again, I might get a slightly different p-value because it's reshuffling these cards here. So I think I had 18, there, 8,000 before. So right tail, again, oops, that's not a p-value yet until I enter the sample statistic from the original sample, 2.62. Okay, this time I get 0.019. Right? Every time you run a randomization distribution, it's going to be a little tiny bit different. Whereas the central limit theorem, there's just one answer from the central limit theorem, aside from rounding error, which we all experience depending on how we round our numbers along the way. And there were a whole bunch of steps here, right? I had to find the means. I had to find the standard deviations. I had to find the difference in the means. I had to find the degrees of freedom. I had to find the standard error, then the t-score, then finally the p-value, right? So there's lots of places to round in between that can lead to this number being a little bit different for one person than another, but they should be in the ballpark of each other, around 2%. All right, so that was randomization hypothesis test versus central limit version of the hypothesis test, which central limit theorem, I highly recommend using a spreadsheet. Can you do some of this with a handheld calculator? The answer is yes, except for the p-value. Then you need a t or normal distribution calculator like StatKey or like the spreadsheet provides, like the formulas related to t-dist. So a regular calculator works only to a p-value, then we need some kind of special calculator.